Namaskara. In this session, we will complete our discussions on Karasubas algorithm and the kind of analysis that we will encounter in problems similar to Karasubas analysis. So, we will look into the details of dealing with the recurrence. T of n is A times T of n by B plus some constant plus order n power d. How do we deal with this kind of recurrence equation? We have to work on a special infinite series for n. Okay. So, in order to get to that special infinite series, the infinite series will be of the form b power k plus some constant z. So, this b power k, if n is b power k plus z, I want the z to be having a property that this n by b plus c must be of the form b power k minus 1 plus z. So, that this term resembles the other term for n. I want to choose z in such a way that n will be of the form b power k, therefore, n by b will be b power k. So, what I want is that if you look at n by b plus c, n by b plus c will be b power k minus 1 b power k minus 1 plus z by b plus c, and I want this to be b power k minus 1 plus z. Therefore, this implies I want z such that z equal to z by b plus c. So, you have to play around with the numbers. Okay. You have b and c, this is known. In what way I have to choose z so that I have z equal to z by b plus c. So, if I have one such z, then I am going to define the infinite series by b power k plus that z value, then it will work. Okay. That is because n by b plus c is nothing but b power k minus 1 plus z by b plus c, but I know that z by b plus c is z, the value is chosen. So, given b and c, how will you choose z? Just solve for that. Okay. For example, if b equal to 4 and c equal to 7, b equal to 4 and c equal to 7, all right. So, I want z equal to z, therefore, z times 1 minus b is 4, 1 minus 1 by 4 should be equal to 7, that is z times 3 by 4 equal to 7, therefore, z is equal to 28 by 3, but I want z to be an integer. So, just take the next integer, it should work. Okay. Play around with that, and because we are taking seal floor, z equal to 10, okay, then you take z equal to 10 and that should work. Okay. Exact value should be 28 by 3. If that itself is an integer, it is fine. If that is not an integer, take the next number, then that will have the upper bounding property with a similar term. Okay. So, this is the crucial way to handle the recurrence, which is given by some shift of certain constant. all we have to do is that figure out a suitable infinite series defined by some powers of B plus some value, and that must satisfy this condition. Okay? This is the crucial condition that the Z should satisfy. If you could work with a constant like this, then so for example, we had in our example n by 2 plus 1. So, B was 2 and C was 1. So, let us see what value of Z is. So, Z equal to Z by 2 plus 1. That means Z equal to 2. Z equal to Z by 2 plus 1 means bring Z on this side. You see that is the reason why we worked with the infinite series 2 power k plus 2 worked for us. 2 power k plus 2 worked for us because of this property that we want to maintain. Okay? So, in general, if you have T of n as A times T of n by B plus C, choose Z satisfying this condition, then work with an infinite series of powers shifted by the Z value, then it will work. You will be able to derive, much like you are deriving the master theorem, you will be able to derive, simplify, you will be able to do everything in a more convenient fashion. So, summarizing, if T of n is A times T of n by B plus C plus n power D, choose n of the form B power k plus Z, where Z equal to Z by B plus C, an integer satisfying this, then it works. Okay. So, it is a small bit of a detail about the algebra, but then it will make the analysis cleaner, and without kind of a hand waving, we will be able to proceed in a cleaner way and conclude about the order of T of n. Okay. So, to summarize whatever we have seen so far, okay, merge sort, it is a canonical example, and then we have seen that for the analysis we can use powers of 2 and monotonicity, or you can do guess and verify, or you can directly solve. Exactly you can try to figure out. So, we have seen all the three techniques for the analysis of merge sort. So, in general, divide and conquer algorithms are recursive algorithms. So, the complexity of the recursive algorithms will be expressed in terms of a recurrence equation. How do you deal with those recurrence equations? Sometime you may be able to solve exactly, in that case you have T of n in closed form, but oftentimes that may be either difficult or you may not get a proper form. In that case you can get upper bound and lower bound by guessing and verifying, or you can get the pattern for a suitably defined infinite sequence, and then you can use the monotonicity to conclude about the order of the complexity function. All those details we have seen for merge sort. Then we were trying to look into the design of efficient algorithms using divide and conquer paradigm. So we have found out min max of n numbers, a1 to n. The direct divide and conquer algorithm had complexity 2n minus 2. This is the direct one. But when you bottom out at a larger subproblem, so we have handled the base case 1 and 2. So we are bottoming out at a larger subproblem. You do not further divide. When you encounter even certain larger problem, solve directly and then use the answer rather than splitting further. When you use that approach, the recursion tree becomes smaller. You do not fragment the input into too many smaller subproblems, and that brings in efficiency. So see whether it gives an advantage to bottom out at a larger subproblem. When we did that, we could get 5n by 3 minus 2 algorithm bottoming out over larger subproblem. When we did that, we got some efficiency. Then typically when we were discussing the divide and conquer algorithm, we were trying to split equally or nearly equally, right. Such a split may not always lead to an efficient algorithm. There are cases in which a carefully studied or worked out split will lead to a much better algorithm. So you ask the following question: is the current split a good split? Is this the best way to split, or is there any other better way to split and get a more efficient algorithm? So you question on splitting, okay, clever splitting. We have found out that for the min-max problem, a very clever splitting is possible, which would reduce the complexity to 3n by 2 minus 2. This is using clever splitting or clever dividing. Okay. So these are the ways in which you can look for improving a divide and conquer algorithm. You may come up with a simple divide and conquer algorithm. If that is good enough, you can take it, but if that is not good enough, then you are looking for opportunities to improve. You want to get more mileage out of an idea. There is a technique, you want to get the best use of that idea. So here are the ways in which you can potentially improve. Look for clever splitting, look for bottoming out at a larger problem. All these things are illustrated by the min-max case study. Now all these things we have done for splitting the problem, if splitting the input into two parts. If we are trying to relate the problem of a given size to the problem of smaller size, it may involve several problems of smaller size. Okay. So that is where we were formulating the recurrence equation of the type T of n is A times T of n by B plus combining cost n power t. This is the size of the smaller problem and this is the number of problems. what Karasva algorithm has taught us is that by reducing the number of problems, we can gain efficiency. When B is 2, you can't make it any smaller. Minimum you have to split in 2. Therefore, you see the ratio 2 you cannot reduce, but A perhaps you can reduce. If you do that, you get more efficient algorithm. So, focus on number of subproblems to be solved. This is another way of improving divide and conquer algorithms. You will still have a divide and conquer algorithm, but you are going to get more efficient algorithm with these kind of approaches. So, this gives us a way to think. Algorithmic thinking means you have to come up with a clever method to solve the problem more efficiently. What are all the ways in which we can think? Where all we can explore? All these case studies give us valuable insight. That is what we have learned so far based on the case studies we have seen so far. Now we are going to look at another magical and very exciting and interesting technique to speed up divide and conquer algorithm. Okay? This technique is called more for less idea. It is a very powerful idea. This is especially suitable for divide and conquer or recursive algorithms. Okay? This will almost look magical. To begin with, it will look little counterintuitive, but with a bit of a practice and grasp, you will see that this is indeed a very powerful and very clever way of thinking and arriving at a solution. It is a kind of slightly out of the box kind of a technique. Okay? So, let us see the detail and let us see how this in general works. Okay? Your basic divide and conquer algorithm, let us say for a given input you have to get an output O. Normally what we do is that we split into I1, I2, and for this we get O1, for this we get O2, we combine O1 and O2 and get the output O. For every input, the output can be obtained in a typical divide and conquer, split the input, solve the problem for the smaller inputs recursively. So, you will have the corresponding outputs, use those outputs or solutions to get the solution of the original one. Now, this can be taking more time, this might take more time, but if I change the specification, I will now change the specification in this way. From I you get not only O, you get some additional values as output. So, change the specification to, for an I want O, X, Y and Z, right. Actually what you want is O, but mathematically you now change the specification to X, Y, Z. These are redundant additions, but you want more. This more can be obtained with less time. In other words, when you change the specification like this, suppose you split the input to I1 and I2. So, when you solve I1, you are going to get O1, X1, Y1 and Z1, and when you solve I2, you are going to get O2, X2, Y2, Z2, because this is the specification of the problem. Recursively when you solve, you will get this. From this you try to get O, X, Y, Z. okay, and this is going to be more efficient. Very counterintuitive. Computing O itself is hard. How can computing O and some more values could become easier? That is because of the interdependency between X, Y, Z and O. Computing the 4 values, because they mutually help, from the 8 values, because you have more information, it is very easy to manipulate them and then get this, rather than using only O1 and O2 and generate O. You may have O1 and O2 may not have sufficient information, that you have to work a lot more in the combining phase. So the combining cost could be a bit more, and that may contribute for inefficiency, or that may contribute for higher cost. Whereas it might so happen that computing O, X, Y, Z is lot easier from O1, X1, Y1, Z1, O2, X2, Y2, Z2. In that case, the combining cost is significantly reduced. When the combining cost is reduced, the recurrence equation will have the combining cost part reduced. Therefore, the solution of the recurrence equation also will have a lower order. Okay? So this is what we are going to see with a case study. We are going to see a very interesting example where what you want to solve can be solved efficiently by demanding some more values may also be obtained. Of course, you can ignore X, Y and Z. But when you write a program with X, Y, Z, everything, these are all the part of the code. So your program works on those values, but the overall code will be lot more efficient than the one that is working only for the output O. Okay? So you might have already felt that it is a bit counterintuitive. If obtaining O for an I is expensive, how can obtaining for I O, X, Y and Z, some other additional values, could become cheaper? Okay? We will see an example and a case study, and that will give us some insight on to how you should choose X, Y and Z. If you choose mindlessly, it will become an overhead. Obviously, you will require more work. But if you choose X, Y, Z in a careful manner, it may lead to a more efficient solution. That is what our case study aims to explain. Okay? We will look into the detail of the case study on more for less in our next session. Thank you.